Every forecast this year has been about the Pacific. A Super El Niño is building. It will be one of the strongest on record, and by December everyone will have heard about it. While that was being tracked, the Atlantic did something else. A band of water along the equator went cold. It is now sitting between 2 and 5 degrees Fahrenheit below normal. If it holds through the season, it will be only the 6th event of its kind in more than 40 years of records. 2 to 5 degrees does not sound like much until you remember what an ocean is. To cool a band of water that size by even 1 degree, you have to move an amount of heat that has no useful comparison on land. Oceans do not change temperature quickly. An anomaly this size means something structural has shifted, not that the weather has been unusual for a few weeks. The part that should bother you is not that it happened, it is that our models are demonstrably bad at seeing it coming, and this is not a small thing to miss. The cold band runs for thousands of miles along the equator. Hurricanes need warm water, and that band decides where they form. Rain for tens of millions of people right across the ocean depends on it too. This is not a detail. It is one of the 2 largest things happening in the Atlantic right now, and the forecast did not have it. What follows is not really a video about the ocean. It is about a blind spot we have known about for years and have never been able to fix. Before anything else, a correction, because it will be the first comment otherwise. The cold band in the Atlantic is not La Niña. La Niña is the cold phase of the Pacific cycle, and it lives in the Pacific. This is a different ocean and a different system with its own name, the Atlantic zonal mode. Zonal means along lines of latitude, which is exactly what it looks like on a map. A band running east to west along the equator. Like the Pacific cycle, it swings between a warm phase and a cold phase every few years, and the cold phase is called the Atlantic Niña. The confusion is not accidental. The names were borrowed deliberately because the Atlantic pattern looked like a smaller cousin of the Pacific one, and the vocabulary already existed. That borrowing has cost the Atlantic pattern decades of public attention, because anything that shares a name with something famous gets read as a footnote to it. Same word, different ocean, different mechanism, different consequences. It swings the other way too. When the same band runs warmer than normal instead of colder, that is the warm phase, sometimes called the Atlantic Niño, and it has its own set of consequences. The pattern flips every few years without a fixed schedule, which is already harder to work with than a cycle that keeps time. And here is the first sign of the problem. You have almost certainly heard of El Niño your entire life. Most people have never heard of this one at all. And that is not because it is unimportant. It is because it is the pattern we are worst at. So what exactly goes wrong? Every major coupled climate model runs the tropical Atlantic too warm, systematically, persistently, in the same direction, across every generation of models that has been built. It is one of the most stubborn known errors in the field, and it has survived decades of improvement everywhere else. The size of it is the part that matters. In seasonal forecast experiments, the error appears within the first month, and it reaches 80% of its full size within 6. 80% within 6 months is worth sitting with, because 6 months is roughly the horizon a seasonal forecast is trying to cover. By the time the forecast reaches the range it exists to predict, the error is essentially fully developed. It is not a small drift that accumulates slowly at the far end. It is there almost immediately, and then stays. Now think about what that means for this specific situation. The bias makes the models too warm. The thing we are trying to predict is a cold band. The error suppresses exactly the feature that defines the pattern. It is not that the models are noisy here. It is that they are wrong in the one direction that hides the thing you're looking for. It is worth being precise about what a coupled model is, because the word hides the difficulty. It is not one simulation. It is an atmosphere model and an ocean model running together, each one feeding the other at every step. An error on one side does not stay on that side. Get the winds slightly wrong, and the ocean surface responds wrongly, which changes the winds again. Small errors do not stay small. And in the tropical Atlantic, the error compounds in a specific direction. Too warm at the surface means weaker temperature contrast across the basin, which means weaker winds, which means less of the process that brings cold water up. The model talks itself out of the very thing it was supposed to reproduce. This is a known problem with the literature behind it. Papers have been written specifically about why models struggle to reproduce Atlantic variability, and the answer keeps coming back to the same bias. Knowing about an error and being able to remove it are two different achievements, and the field has only managed the first. To see why this is hard to model, you have to see what the ocean is actually doing, and it is stranger than it sounds. Ask when the eastern equatorial Atlantic is coldest, and the obvious answer is winter. The obvious answer is wrong. The warmest water of the year arrives in spring. The coldest arrives in July and August, in the middle of northern summer, when the surface drops below 77 degrees Fahrenheit. The ocean is at its coldest when the sun is at its strongest. The reason is wind. Along the equator, the trade winds blow from the southeast. Because of the way the Earth rotates, a wind blowing along the equator does not simply push surface water forward. It pushes it sideways, away from the equator, in both directions at once. The surface layer peels apart down the middle, and water has to come from somewhere to fill the gap, so it comes up. Cold water from a few hundred feet down, water that has been sitting in the dark, rises to take the place of the warm layer that was dragged away. That is upwelling, and it is one of the most important processes in the ocean. It is also what brings nutrients to the surface, which is why the equatorial Atlantic is productive enough to feed the fisheries of the entire Gulf of Guinea. And that is exactly what makes it hard to simulate. The temperature at the surface is not being set by sunlight, which a model handles easily. It is being set by wind, by the rotation of the planet, and by how deep the boundary between warm and cold water happens to sit that year. Three things that have to be right at once, in a basin where the models already start out too warm. So the cold band is not water that cooled down, it is water that came up. The first consequence is the one American forecasters care about, and it arrived fast enough that seasonal predictions had to be revised. There is a stretch of the Atlantic that forecasters call the main development region. It runs from the west coast of Africa across to the Caribbean in a belt along the tropics, and it is where most of the season's serious hurricanes are born. Three things have to be present at once for a storm to build: warm water at the surface, deep enough to survive being churned, moist, unstable air above it, and winds that do not change speed or direction too much with height, because a storm that gets sheared apart at altitude never organizes. Remove any one of the three and the season goes quiet. A hurricane needs warm water to form. It needs the heat and the moisture that rise off a warm surface, and it needs them over a large area for days. Cool that surface and the supply is cut at the source. That last condition is why El Niño reaches across a continent to affect an ocean it is not in. A strong Pacific event changes the circulation of the upper atmosphere far beyond the Pacific, and one of the things it changes is the wind shear over the Atlantic hurricane belt. The storm never forms, and the reason it never formed is thousands of miles away. And here is where the two patterns stop being separate stories. El Niño in the Pacific also suppresses Atlantic hurricanes through a different mechanism involving wind shear high in the atmosphere. The cold Atlantic suppresses them from below. The two do not cancel each other out, they add. Both are pushing the atmosphere in the same direction at the same time. That is why forecasters have revised their numbers downward, and why NOAA has said openly that the two patterns are working together to reduce activity this year. A quiet hurricane season sounds like good news, and for anyone on the American coast, it is. It is not good news everywhere. Almost every story about this pattern stops at hurricanes, because hurricanes are what the American audience is watching for. The larger consequence lands somewhere else. The same warm equatorial Atlantic that feeds hurricanes also feeds the rains of West Africa. Moisture rises off that water, moves inland, and becomes the monsoon that the farming of the entire Sahel depends on. Cool the ocean and you weaken the supply at its origin. The West African monsoon is not rain that arrives gradually. It is a front that moves north across the continent through the summer and then retreats. Its timing decides the planting calendar for a strip of land running from the Atlantic coast to Chad. Arrive 2 weeks late and the seed is already in the ground. Arrive weak and it does not matter that it arrived at all. For tens of millions of people, this is not a seasonal curiosity. It is whether the rains arrive on time, whether the planting works, and whether there is a harvest. It also runs the other way, which is the part that gets left out. When the Atlantic band is warm rather than cold, the rains can be heavier than the ground can take. The pattern does not have a good phase and a bad phase. It has two phases, and the damage depends on which one arrives and whether anyone knew it was coming. And now put that next to what we established earlier. The models are worst in the tropical Atlantic. They are worst in the exact basin where the forecast matters most to the people with the least ability to absorb a bad year. That is the part of this story worth being uncomfortable about, not the ocean. The distribution of who gets a reliable forecast and who does not. There is a second reason the Atlantic is harder, and it has nothing to do with the physics. A model is only as good as what you feed it. To forecast an ocean, you need measurements from inside it, continuously, across the whole basin. Temperature at the surface and at depth, winds, currents, the position of the boundary between warm and cold water. The Pacific has had that for decades. After the El Niño events of the early 1980s caught the world unprepared, an array of moored buoys was built across the equatorial Pacific. It was built specifically to watch the thing that had surprised everyone. It has been feeding data continuously ever since, and it is a large part of why El Niño forecasting improved as much as it did. The Atlantic has an equivalent network, but it came later and it is thinner. So the ocean we understand best is the one we decided to instrument first, after it embarrassed us. And the ocean we understand least is the one where the forecast matters most, to the people least able to absorb being wrong. That is not a physics problem. That is a choice about where to put the instruments, made decades ago, still producing consequences. So where does that leave the forecast for this winter? The honest answer is that the Pacific side is reasonably well understood. El Niño has been studied for over a century. It is monitored by an array of instruments across the entire basin, and the models handle it comparatively well. The Atlantic side is not in that position. We know the pattern exists. We know roughly what it does. We know it is rare, and we know this is only the 6th time in 40 years. What we cannot do is predict it reliably in advance, because the tool we would use to predict it has a built-in error pointing the wrong way. And there is one more thing that makes this season genuinely new. Every previous event of this kind happened in an ocean that was holding more or less steady. This one is forming in an ocean that has been warming year after year, which means the baseline underneath it has moved, which creates a problem that has nothing to do with computing power. A model is trained and tested against what has already happened. If the background state is drifting, then the record it learned from describes a world that is slightly gone. Every event is now happening slightly outside the conditions that were used to calibrate the tool. The old patterns still rhyme. They no longer repeat cleanly, which is a strange position to be in. We can see the thing happening in real time, on satellite, today. We simply could not have told you it was coming. It is tempting to file this under bad news, and the internet is glad to help. That misses the more interesting fact. A gap between what the ocean does and what the models say is not a failure of science. It is science telling you exactly where it is weak in a specific basin, in a specific direction, by a measurable amount. That is more useful than confidence would have been. And there is something worth saying about how this was found at all. Nobody discovered the cold band by running a better model. It was seen on satellite by people looking at what the ocean was actually doing and then confirmed by instruments in the water. The prediction failed and the observation worked. The uncomfortable part is only this. We found out about this one by watching, not by predicting, and watching only works for the things already happening. This video was about why nobody saw it coming. The other half is what it actually does once it is here, and that one is already on this channel. The cold band and the warm Pacific do not cancel each other out. They push the atmosphere the same way at the same time, and the result reaches the hurricane season, the winter in North America, and the rains of West Africa. If you want that side of it, watch that one next.